Okay. We want to talk about indefinite integrals. It's the one thing that you're apparently still having trouble with. So we want to cut through that, okay? Because it's likely to cost you when you take the exam, and kind of did on the test. Okay, so just consider integral from 0 to 1, 1 over x dx. First place, you can't do this in the usual way, because your antiderivative is a natural log, and you would then end up having to evaluate the natural log of 0. And you understand that, okay? So that's not a good thing, okay? Now we could also notice, just conceptually, that the natural log goes to negative infinity as x goes to 0. Now you should understand this about the natural log function. It just helps visualize things, and also if you're doing mathematics in a biology course, it often involves exponential logarithmic functions, okay? And your basic exponential function has a graph that looks like this, and the natural log function is inverse to it, so the natural log function has a graph that looks like this. And you should always have those graphs in your head, along with the graphs of other basic functions, okay? It just helps you think about trends. And you're quite good at visualizing and even in multi-dimensions, so I just kind of recommend that as the kind of thinking that would do you a lot of good. And we can see that as x approaches 0, this thing has an asymptote for the same reason e to the x has an asymptote with the negative x-axis. Natural log has an asymptote with the negative y-axis. It's the inverse function relationship. And if you don't totally know why the inverse function relationship causes the graphs to have this shape, and why the exponential graph has this shape, again, something in all of your spare time, which you probably don't have, but you should look it up. You do Khan Academy. Khan's going to look up inverse functions in Khan Academy. Find where he's talking about exponential and logarithmic functions. Go to his pre-calculus when he's talking about how you have certain basic functions and transform them. Well, that's just context, okay? So what we expect is kind of, if the natural log of x approaches negative infinity, and if substituting the lower limit and the antiderivative would give you something that approaches negative infinity, that's probably going to mean that your integral is divergent, that the integral itself is going to approach negative infinity. The total area under the 1 over x curve is going to approach, well, okay. You're subtracting the lower limit, so the area is going to approach negative of negative infinity or infinity. But the idea that the area under the 1 over x curve, and again, that should be completely obvious to you, that's your 1 over x curve. You got a lot of area up here as you approach the asymptote, okay? And that area turns out to be unlimited, okay? So these are, this is the idea then of an integral that doesn't converge, okay? If your integral is 1 over the square root of x, it would look a whole lot like this, okay? But it would converge. But we'll do that. Okay, I think we've already done some of that. Okay, so let's be a little more specific, okay? So, okay, 0 is a point at which your antiderivative is undefined. So you consider the integral from, I think your book uses C, so I'll use C. Okay? Where C is close to 0. Doesn't have to be close to 0, but that's what's going to get us to this integral, because we're replacing the 0 by the C, so let's let just C be something close to 0. Now, it's also positive, because we can't integrate across a value of x where the function is undefined. And this is the function itself is undefined at 0. So C is close to 0. So, well, the integral from C to 1 of 1 over x dx is, what's the natural log of 1 minus the natural log of C, right? So it's just negative natural log of C. Natural log of 1 being 0. Okay? Now, C approaches 0. Let's say, well, yeah. Okay, natural log of C approaches negative infinity as C approaches 0. So negative natural log of C approaches infinity, right? So if we go to the picture of our 1 over x function, you know, if x is here, well, we just have this area. It's a finite area, right? Now, if x goes closer, well, it's going to have a, you know, it's going to come up much higher. You're going to have a bigger area, right? Okay? And the closer this point gets to 0, we'll call this point C, right? So I see, the closer this C gets to 0, the more area you have. Okay? That doesn't necessarily mean that the area is unbounded, but in the case of this function it does, and this proves it. It just means that as you keep getting closer and closer to 0, there's no limit to how big that result gets.